Here I will try to explain the formal definition of a limit and work through a problem you might encounter on the topic. The limit definition states that given f of x defined on an open interval about x naught, except possibly at x naught itself, limit as x goes to x naught of f of x is equal to L if for all epsilon greater than 0, there exists delta greater than 0 such that for all x, if the distance of x from x naught is less than delta, then the distance of f of x from the limit L is less than epsilon. We typically say that the limit of a function at x naught is the value that f of x approaches around as x goes to x naught. But what does it really mean to approach a value? For a function to approach a value, it means that we can find it in the vicinity of that value. To state it in more understandable terms, if somebody goes to, say, a grocery store at noon, then we would expect to find that person in the vicinity of the grocery store at noon. So this is an example of a function, and we are examining its value or its limit at point x naught. To define the vicinity of the function's value at x naught, we can look at the vicinity around its limit L. So we would draw an interval around L, say L plus epsilon and L minus epsilon. And that's the vicinity we're gonna examine. Whenever the value of x approaches x naught, we want to find our function in that vicinity. And so in the case of x approaching x naught, we're also defining an interval, say x naught plus delta and x naught minus delta. So in a way, we are able to put our function into this box. We are able to put bounds on where we expect to find our function at a certain point. Furthermore, as we make our epsilon smaller, thus reducing the interval, we should be able to make our box smaller and smaller and still find the function in the vicinity of its limit. To illustrate it further, we can look at a function whose limit does not exist at x naught. In this case, we would be dealing with a discontinuous function. In this case, if you were to look in the vicinity of where you might imagine the limit would be of such a function, then if you made the box small enough, all of a sudden you would find that the function is not always in the vicinity of the limit that you might think it's approaching. Because instead you would find that the function hangs out in a different box. For example, if someone were to say they were going to a grocery store at noon, but instead they went to a movie theater, then obviously they're not going to be at the grocery store, so we can't say that that person is approaching the grocery store at noon. And similar with functions whose limit does not exist, or if we look at a wrong limit, value of the limit, then we simply won't see the function hanging around the value of the limit at a point x naught. Now I will do an example problem. So here's the problem statement. I'm given function f of x, which is equal to x squared. I'm given L, x naught, and epsilon. And I'm asked to find the open interval given by the inequality f of x minus L less than epsilon. And then I'm asked to find our delta. So in this case, L is the limit that the function approaches, x0 is the value at which we're looking for the limit, and epsilon is how tight the vicinity of the function's values that we're looking at. Okay, so for part A, I'm gonna solve f of x minus L in absolute value less than epsilon. We can get rid of the absolute value by writing it as minus epsilon is less than f of x minus L less than epsilon. Then plugging all of our values in, we get, from here we can simplify this equation by adding 4 to all sides. And then when we take square root of both sides, we will get two answers, plus and minus. Because when we take a square root of a number, say if we take square root of 4, it's going to equal to plus or minus 2. So we will get the following two inequalities. We can interpret them graphically. So we'll have the interval here and the interval on the positive side. Note that one of the intervals contains our x0 value, which is equal to minus 2, while the other one doesn't. So since this is the case where we are looking for the limit, we don't care about the interval that does not include our limit. So the answer to part A is going to be that the open interval given by the inequality absolute value of f of x minus L less than epsilon is going to be minus 2.12 to minus 1.87. From here, they want us to find delta. If you remember, graphically, we want delta to be a value such that if x minus x0 absolute value is less than delta, then we would want our f of x minus L in absolute value to be less than epsilon. So we want to find delta such that it will produce an interval about x0 such that any value taken from that interval would always land within the distance epsilon from our limit. So more concretely, we would need to solve the following two equations. x0 minus delta is equal to minus 2.12 and x0 plus delta equal to minus 1. And x0 plus delta equal to minus 1.8, where the values have been taken from the interval bounds from part A. So plugging in for x0, we get minus 2 minus delta is equal to minus 2.12. And here we would get minus 2 plus delta is equal to minus 1.8. Solving for delta, we get delta is equal to 0.112 and delta is equal to 0.13. And in this case, we would choose to take the smaller value of delta since the interval 2.12 minus 1.87 needs to be contained within the interval minus 2 minus delta and minus 2 plus delta.